Okay, today I'm doing a quick video on speed of sound and how to calculate it. So, speed of sound is, as you know, the at the rate that sound travels through a substance like air or water or steel or some type of gas, whatever it may be. And all you need to know is some of the properties of that gas or fluid or material in order to calculate it. So the equation for the speed of sound is going to be A, which we're going to call the speed of sound, and that's equal to gamma R T G sub C, and it's the square root of this quantity. Now you may know from other videos that gamma is equal to the ratio of specific heats, and for us that's going to be 1.4, and then R is our gas constant, and we are going to use 53.36 foot-pounds force per pound mass Rankine. And then our temperature, that's going to be our variable in this case, our variable. And this variable is going to allow us to calculate different speed of sounds in different temperatures. So our temperature, that's going to be our static temperature, not total temperature, but static temperature. So I'll do a couple examples, and then our G sub C, almost forgot that. That is just our conversion factor of pounds mass to slugs, and that's 32.174. And this one, units are in pounds mass feet per pounds force second squared. So we got some screwy units going on, but you'll see how they work out in a moment. So let's do an easy example here. Let's say that we are at sea level, so we'll say our altitude equals 0 feet. Okay, so sea level. And sea level, our T is going to equal 518.69 degrees Rankine. And all the rest of these numbers will be the same at sea level. So let's go ahead and calculate the speed of sound. So we're going to have 1.4, which is our gamma. And then we have R, which is 53.36 foot-pounds force per pound mass Rankine. And our temperature, which we decided standard sea level temperature, 518.69 degrees Rankine. And then our conversion factor, G sub C, 32.174 pounds mass feet per pounds force second squared. Okay, I'm just going to raise this to the 1/2. It's the same as the square root. Okay, and this is going to work out to be 1116.55. Now, what are our units? Well, we've got pounds force and pounds force, so those two are going to cancel each other. We've got pounds mass, those are going to cancel. We got Rankines, those are going to cancel. And so we're left with feet times feet and second squared, so foot squared over second squared. And we're taking the square root of all of this, so this 1/2 power is going to cancel the squares. So we're going to end up with, feet per second. And that is going to be our speed of sound at sea level. Okay, so let's say that we're now at, how about 40,000 feet? 40,000 feet. Okay. Um, so at 40,000 feet, I have some tables from one of my textbooks, and 40,000 feet, our pressure is going to be a little bit different. We're not going to use pressure, but I'm just going to explain it to you anyway. Our pressure is going to be 2.73 psia. Now, at sea level, I should write it up here, but at sea level, our pressure is, for comparison, 14.696 psia. So a huge pressure drop there. Our temperature, our static temperature, is going to be, let's see, where is it? 390.003 degrees Rankine. So as compared to our 518, this is much smaller also. And so we went up in altitude, it got colder. So with these new properties, we don't need pressure, but just comparison. Anyway, we can calculate the speed of sound at this altitude also. So our gamma is going to be the same, and then our R, which is also going to be the same, is going to be 53.36. Now, I'm not going to write the units in here because it gets messy, and I already showed you how they work out, so I'm just going to write the numbers in here. But I do encourage you to always write your units, especially if you haven't made a particular calculation first, because it could help you figure out what's wrong if you don't get the right answer. And our temperature and our G sub C. Okay, and to the 1/2 power. Okay, and this speed of sound works out to be 968.19 feet per second. Now, why is this speed of sound less than this one? Well, because of the temperature. Our temperature at 40,000 feet is, let's see here, our temperature here is a lot less than 0 feet. Okay, and that's basically the only thing that's changed here in this situation. Pressure really doesn't matter, it just has to do with temperature. So, as you can see, you're going to get a different speed of sound depending on the temperature and the gas properties. So, you know, helium's going to be different. You know, it's going to vary. So it's not just a constant number.